Thank you. What a great pleasure to be here. First time in Asia, actually. And I was told to prepare about a half an hour, and I prepared far too much material. I'm going to jump around as quickly as I can, hopefully tie in everything together by the end. I'm going to start with just an audio clip, if possible, actually two of them, and you get the gist of what I'm talking about. This is from the last movement of the Fifth Bartók Quartet. You can hear two versions. Now the other version, same piece. Okay, big surprise in between. That's what I want to talk about today mainly. Everything is expected in a piece of music when we're writing. It gets boring very quickly, and I often say, what do I need to hear the last half? If it's identical to the first half, or it's been repeated 50 times. I don't need a 51st time, and as you all know, probably that's minimalism, which I've never been so fond of. Those are some great pieces that I love. Just to me, it's not really composing. On the other hand, music, I don't want to mention names, but it's so complex and nobody knows anything. That also gets boring because nothing's set up. The listener never expects anything, he doesn't know what to expect. And this is going to be the point of this. I learned relatively recently, and this is the way I've been composing all my life without being aware of it. It's in probability. It's called Markov chains, which means that the coming events are going to be dependent on what came before. I love mathematics. That's why I'm an amateur mathematician. That comes from the word love. Thank God I'm not a professional mathematician. I probably would stop loving it. But I've never studied probability. My interest has been in algebra and number theory. Real art of mathematics. So for me, I want to mention what I find between mathematics and music is the aesthetics. I can get such a high out of listening to a beautiful passage of Bach, or an incredibly wonderful high from reading a proof, or even a little fragment of a proof. What a fantastic step. I'm going to show all those things today. As far as using mathematics as a compositional tool, I've never done it, but I don't disparage anyone who does. For me, composing is just unbelievably difficult. I hate it, but it's the only way I know how to make a living now, so I do it. And it gets harder and harder because history has gone on, and everything's basically, for concert music, using traditional scales, traditional instruments, pretty much I think everything's been done. And we're running around in circles some way. I'm going to point some of these things out too. Mathematics and music in our department at the University of Michigan, Performance Arts Technology, the students are required to study a tremendous amount of applied mathematics because most of them are going to be sound engineers, or sound architects, and they have to know something, but I've never had this applied to music. One thing that's been common, I've noticed, there was some folklore, I think by a Hungarian musicologist, that he said Bartók wrote his music on Fibonacci series. Well, I've heard that about some of his pieces. So we had an applicant one day say, you know, Bartók wrote his music on Fibonacci series, that's what I like to do. And I said to him, I was lying, of course, I'd never heard that before, that Bartok used Fibonacci series. And I said to him, you know, Beethoven used Fibonacci series? And he flabbergasted. He said, no. I said, all the time. So I had a volume of Beethoven sonatas in my studio, and I said, here, pick any sonata you want. And he happened to pick the first one, and then I showed him right on the spot. This is the first Beethoven sonata. I should have practiced, but I didn't. And you can see what I did below to show him how this is based on Fibonacci series. Now, of course, this is total nonsense. And I want to show you some other things, or talk about some other things I've had as a teacher, where I find this total nonsense. Maybe you've heard of the time point system invented by Milton Babbitt. Milton Babbitt, I've met a few times. It surprised me. He was an authority on Broadway music. He knows every Broadway tune since the 1920s, probably. But if you know his music, you'd never believe it. Anyway, he invented this thing called the time point system based on writing rhythms with a modulus of number 12 to be concurrent or with the 12-tone system. Now, it's totally arbitrary, and to me, it's total nonsense for that reason. Could have chosen any number if you wanted to use a time point system. Another one, I think the funniest student I've ever had brought in a piece using the number pi, mod 12. That is, he divided pi by 12 and used the remainders as pitch classes, 0 being C, 1 being C sharp. So I don't know if the music was worse or the mathematics was worse, but they were both pretty bad. Now, what really got to me, I was about 14, was this. In Detroit, where I grew up, you couldn't escape the math curriculum. I had to take algebra in 9th grade, geometry 10th grade, et cetera, et cetera. But my 9th grade teacher knew I was very, very interested in mathematics, and I'd been going on my own since the 6th or 7th grade just learning, and he encouraged me to study calculus, and he would help me. And I was just playing around, this is possible, this is possible. And I came up with this, quite by accident, just by, I took a derivative of the arctangent function, and then I integrated it, and I got this. This is just amazing. How could a simple arithmetic sequence like that end up with a transcendental number? And I think it was really too much of my life where I felt, like I heard it said once about art, it's somewhere between science and religion. And that was the first time I felt that in mathematics, too. I haven't studied a lot of applied mathematics, but for sure in pure mathematics. And this is just an amazing, amazing thing. And of course, the most beautiful formula said is that E to the I pi equals the number of 1. That flabbergasted everybody. When I went to school, E was taught only in college. At that time, people weren't taking calculus. Pi was taught in the 6th grade as far as geometry. In the 11th grade, our second algebra class, we learned about I. So 3 constants coming from totally different worlds, at least at that time I thought so. And there's this beautiful relationship, E to the I pi equals -1. When I hear music, it's beautiful, it's really, really moving. I get the same feeling as seeing that. I'd like to go next. By the way, I'm told I've got to get a 5-minute signal to stop, so if they don't show it to me, start whistling or something, okay? Could you go to, please, the cotangent function? This is something I saw relatively recently. The author of the book, it was a book of proofs, beautiful proofs, didn't describe who actually found it. He just said it was someone in England, I think at Oxford. And because of time, I don't know, for mathematicians who just see the first line, they'll say, well, that's obvious. For non-mathematicians, I'm not going to have the time to go through it all, but I gave a little sketch of the proof here using the moi. Go down the first page and see how I just took the imaginary part and came up with an example for a function of 2. I can go to the next page, please. Newton's identities are very useful here. And Newton's identity says that the sum of the roots of a monic polynomial are going to be negative b. There's the n minus 1 term. And so the first time I did, I used to solve the quadratic equation but this is much more useful for the general case, which is up here. So using the same tools as before, I have the general case and I prove the theorem for cotangent squared function. Then, very simply, one can go on because cotangent squared plus 1 equals cosecant squared. And just by adding m to both sides, you get the 1, 2, 3, 4 on the fourth line there. And you get the 2m times 2m plus 2 over 6. Now I just fiddled a little with it arithmetically. You'll probably find out how I get to the next line. And then, if you realize as m approaches to infinity, both the coefficients of pi squared over 6 equal 1. And you get the beautiful formula that was first discovered by Euler. Interestingly, his proof at the time was almost totally unjustified, and he knew it, and I think a few years later, he made another proof that would satisfy everyone of his day, though I understand that Euler was quite famous for throwing caution to the wind that way, those proofs. The next thing I wanted to talk about is musical stasis, Western music. I noticed when I was in school that since Middle Ages, what distinguished Western music was harmony. No other music of the world that I know of, I'm not a musicologist, has developed harmony like the Western music has. Of course, we've had to sacrifice that, and we have relatively naive rhythms and melodies that have to fit into the constrictures of our notation system. But a lot of harmonic development has been amazing. Unfortunately, as harmony developed through the time of the Renaissance, or using triads, multivariate, seventh chords, so forth, ninth chord later on, we got more and more notes, and eventually by the early 20th century already, we have functional chords with about 12 pitches in them. You have something like this. Sung together, 3 diminished seventh chords played at once. It's not, so chords are tone clusters, but that's the easy way. But you have functional harmony using all 12 notes. So I thought to myself, if Western music parallels the development of harmony so closely, where should it go? And tying it into mathematics, I thought to myself, well, this is kind of a Galois argument between groups and fields. That if it couldn't go about a fifth degree equation being solvable, the group wasn't solvable, the equation wasn't going to be solvable. So that's what I felt. Using 12 notes, where do we go harmonically? And the answer I found was it's a big problem. I've noticed today more and more with the students that music is getting simpler and simpler and simpler, and film scores are getting simpler and simpler and simpler. I'm really wondering what the future is going to be. Could you go to the next slide, please? Good. Schoenberg said there's plenty of music left to be written in C major. And it's true. You could always write a really great piece in C major, but he would simply do it and submit it as serious Schoenberg. I think composers today wouldn't do it, and I think the piece in C by Terry Riley from the 50s was sort of just a knee-jerk reaction to what was going on, and it was an early minimal piece. I saw this, I forget when this theorem came out in the 60s called the seventh circle theorem. And it's neat, you can put the circles outside the big circle or inside the big circle, and you'll notice that the diagonals are going to be concurrent. And this is described as a really, really beautiful theorem from Euclidean geometry, and the proof, if you ever care to go through it, it's unbelievably ugly. And I've read that most first proofs of theorems are ugly, and then going through the generations, simplify it. But no one bothered with this at all to find a more simple proof. Why? Because it's another theorem from Euclidean geometry. And what's the interest in doing that? The next thing I want to get to is talking about what makes masterpieces in music. This is all going to be tied together, believe me. So I was wondering if we could go to the Clive Bell quote. Great art remains stable and unobscured because the feelings that it awakens are independent of time and place, because its kingdom is not of this world. To those who have and hold the significance of form, what does it matter whether the forms move them were created in Paris the day before yesterday or in Babylon 50 centuries ago? One of my favorite questions that I ask applicants at the University of Michigan If Beethoven had written Symphony 1 and 2 and 4 through 9, and some guy off the street happened to write the third symphony, the Orchestra Symphony Re, would it still be the great piece it was? Now, to me, there's no question. But I'm amazingly in the minority. I ask students and I ask my colleagues, they all say no. That somehow the time that was written has to do with it. If anyone can explain why anyone would think that way, I would love to hear it. Because I hold just like 5 bell holes. What does it matter when it was written? People will say, well, you know, it's been done already, and it's like the 7th circle theorem. We don't need another piece of tonal music and start with Beethoven. So I've wondered if such a thing could ever happen in mathematics. That way, where we think that we have a theorem, and it's no longer relevant. It's no longer true. We have different standards of rigor in the proofs, but a theorem is either going to be true or not true. And to me, a masterpiece of music is going to hold the same thing. Of course, what is a masterpiece is going to depend on the person hearing, of course. If I happen to hear a rock song or a rap song, it might be okay, but it doesn't quite hold up in my line of thinking as great music. Though I find some folk tunes incredibly beautiful, and I can hear them over and over, you know, with the tunes repeated 10 times and not get bored. Look go to the next slide, please. I'm going to relate this to the prime number theorem. This was first conjectured by Gauss. Slide. Oh, I'm sorry. Thank you. Thank you. How am I doing on time, by the way? 10 minutes? 10 minutes? Okay. This is a history of the famous prime number theorem. That n over long n is going to approach the number of primes as n approaches infinity below n. It wasn't proven officially until the early 20th century in a very, very difficult proof using complex variable theory. And there are more proofs on this, as I wrote similar ones. 30s, Norbert Wiener's proof had an electrifying effect, naming that an elementary proof could eventually be found. His proof wasn't easy, but it gave an opening to it. First elementary proof is from Erdős and Silberg, and it was interesting, they called it a simple proof because it didn't use complex variable theory at all, just the what's required to understand prime numbers, but it's 50 pages long of a simple proof. It's hardly simple in that sense. Finally, in 1960, Norman Levinson proved a simple enough proof to be taught in an undergraduate number theory course. So this was a major, major theorem in number theory, proving people working on it. After 1960, people stopped working on it. Why? Well, I thought it's like the 7th circle theorem, or like classical music. What more could be added? Can make still a simpler proof? So what? What does it matter anymore? So I think very, very strongly this has happened in our world of classical music, which is why in about my mid-20s I stopped writing classical music almost altogether. I turned to folk music, and I have a notated folk music. That's kind of my style of music. Next thing I wanted to talk about is originality. What's original? I think nothing can be original anymore. In fact, I don't think anything was much original by the time of Beethoven already. I like to say that anything that Beethoven wrote, Haydn did first. I'm going to give a perfect example if I could. Everyone knows. People don't know this. line, I think King Solomon said it, Ein kol chadash mitachat hashemesh, there's nothing new under the sun. And here's a perfect example about that. About the Fifth Beethoven Symphony, I'd like to talk about that because the material in the first movement is just really, I would say, terrible. But it's, what is it? It's nothing, really. I just play this, ba 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 ba, and ba da 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 da. What makes this piece so incredibly great, this movement? It has to do with form. That's what I was talking about at the beginning, with the idea of Markov chains. Beethoven sets us up so many times. Unfortunately, we're so used to it now, it doesn't make any difference. Stops. You have no idea whether it's going to be a fast or a slow movement. And he's keeping us on our toes by that. Now, today we still love it, I think, but we're used to it already. There's just so many amazing surprises. The first cage, actually. Orchestra cuts off, and the violins aren't watching, it looks like, because they hold on. And the second time, in the recapitulation, at the same place, you think the violins are going to do it again or perhaps get it right, but instead the oboe holds on and starts playing a cadenza. I mean, it's just really crazy, and I can't imagine what it would have been like at that time. So, with the time left, I'm going to play another excerpt, just like I did at the first, also from Beethoven. This is from one of his quartets. And talking about this whole idea of a Markov chain where you set up. Both these pieces are about 30 minutes long, and I'm playing near the end. So you have to imagine, especially with the Bartok one, where he has a silly tune, which is actually it's a diatonic representation of the main theme of the piece. But that's unimportant. I'm going to play this now to end up with this, and we'll hear how Beethoven did the same thing. There's fourth movement of 59 number 3 quartet. Great ending of a 30-minute piece. Everybody, in fact, the first time I heard it, at that point I was already ready. I was halfway up to start screaming and clapping my hands. I think I heard it when I was 16 years old. I was just amazed. Clip 2. There's the Budapest Quartet back from 1953, I think. So, to finalize everything, every phrase of music, every note, every rhythm is setting us up for what is to follow. The idea is to be surprising, to be boring, what they're expecting, give it to them once or twice, and then surprise them. I don't know if there's any answer to the ratios of each property you should use to accomplish this, but I think that Beethoven does it all just by puts it right in the right place for everybody to be standing up ready to scream and then being disappointed by that sudden stop. Okay, I think we're up. Thank you.